We've talked about several test time scaling tricks recently. Today, we're diving into another one, Recursive Inference Scaling, or RINS. So, what's the trick? RINS takes part of the model and loops it on itself, refining its own outputs before passing them forward. It achieves better accuracy, lower perplexity, and even a plus 2% boost on zero-shot ImageNet. Now let's dive in.
Let's dive into Recursive Inference Scaling, or RINS for short, and I'll use RINS going forward. The core idea is pretty neat. Think of a standard neural network as a conveyor belt in a factory. The data, or product, goes through each stage exactly once, and out comes the final result. But with RINS, we take an early part of the network and run it multiple times before letting the data continue on. It's like adding several quality checks early on, ensuring the product is refined before it moves to the end. Why does this help? Language has repetitive, self-similar patterns across words, sentences, and paragraphs. By looping over the first few layers multiple times, we can capture those repeating structures more effectively. Interestingly, the paper compares different ways to apply recursion. One approach, called repeat all over, just reruns the entire model from start to finish. But that can be overkill in terms of computation. Instead, focusing on a specific section of the model often yields a better trade-off between speed and accuracy. What's really appealing is that RINS doesn't alter the model's size or how it's trained. It's purely about reworking the inference process, making it a cost-effective add-on. It's also flexible enough to be applied in multimodal tasks, like vision language scenarios. They even discuss a stochastic twist on RINS, where the model sometimes skips these extra recursion steps to balance performance and cost. This setup provides most of the gains without always paying the full compute price, and the paper teases that we'll see more about this down the line. Now let's look at why RINS might be a big deal. Traditionally, if we want better model performance, we often train longer or scale up the model size. But RINS offers a different path. It improves performance without adjusting model size or training time. Picture the neural network as layered decision-making. The usual flow is straightforward. Each layer handles the data once, then passes it on. With RINS, we pick an early block of layers, repeat them, and only then proceed. It's like a composer revisiting a melody over and over before layering on the harmony. The paper compares RINS with a method called repeat all over, or RAO, where the entire model is repeatedly applied. RAO can deliver good results, but it consumes a lot more compute. RINS focuses the extra computation where it's most beneficial. One of the most interesting parts is how stochastic recursion can make RINS adaptable. Instead of applying recursion a fixed number of times, we can randomize how often those loops happen. That means you can dial the recursion up or down on the fly, depending on your system's constraints. They also point out that RINS extends to tasks beyond just text. For instance, it's shown to work in multimodal tasks, such as image classification, offering consistent improvements in benchmarks like ImageNet. So it's not just for language. This trick can be quite versatile. Alright, before we get deeper into how RINS works in practice, the paper lays some groundwork to compare different recursive setups. Picture two models side by side, one that does recursion and one that doesn't. If the recursive one gives better results without extra training costs, that's a clear advantage. To categorize various approaches, they introduce two terms, signature and degree. The signature tells you where recursion is happening inside the model. Maybe you have blocks labeled A and B, and you decide to repeat B 2 or 3 times in a row before moving on. That would be something like AB squares C if you're naming the blocks in order. Next is the degree, which tells you if the recursion is at the whole model level or within smaller subblocks. The higher the degree, the more finely you're applying recursion throughout the network. More recursion can improve accuracy, but it also uses more compute. Putting this all together, the authors want to know which recursive structures give you the best bang for your compute buck. They frame it as, can you keep training costs the same, tweak the inference strategy with recursion, and get better performance? If so, that's a win. Now take a look at Figure 2 to see how different models hold up across various amounts of training compute. The horizontal axis is the computational cost, while the vertical axis is loss. Lower means better. You'll notice that RINS consistently stays below the baseline curve, and this advantage becomes more pronounced at higher compute levels. Meanwhile, a long sequence baseline processes fewer examples and ends up with worse performance. If you want hard numbers, Table 1 is the place to look. It shows performance on common sense reasoning tasks, like question answering. RINS outperforms both the baseline and RAO. In some tasks, the improvement is modest, like in Winogrande. But in others, it's a game changer. For instance, in Boole Q, accuracy jumps from 47.7% up to 52.5%. And in Pika, it leaps from 54.5% to 69.5%. All this is achieved simply by restructuring inference. No increase in model size or extra training. This is crucial for scenarios where compute is scarce or expensive. As we move forward, the paper digs deeper into how RINS is implemented to achieve these results. Next, let's talk nuts and bolts. Figure 3 shows a simplified pseudocode for RINS. It's straightforward. You split the model into two main blocks, A and B. Normally, each block handles the data once, but with RINS, block A gets looped a certain number of times before the data even touches block B. They also introduce stochastic recursion here. That means, during training, the number of times you loop block A can vary. Sometimes you do it, sometimes you skip it. This randomness helps avoid overfitting and lets you flexibly decide how much extra compute you want to invest at inference time. Then we have figure 4, where you'll see a graph of compute usage on the x-axis and loss on the y-axis. As you increase the recursion depth, for example, applying block A 2, 3, or even 4 times, performance keeps getting better. But there's a price. More recursion means more computation. Stochastic RINS comes in handy if you don't always want to pay that full price. You can randomly skip recursion steps without losing too much performance. It's a nice compromise, especially useful in real-world setups where compute is often limited. And the authors hint that this idea isn't just restricted to language tasks, but could apply to vision as well. Now, let's zero in on this stochastic aspect. Figure 5 shows different probabilities of skipping recursion, labeled P_skip. When P_skip equals 0, so no skipping at all, RINS yields a clear performance boost over the baseline. But as P_skip grows towards 0.5, the advantage diminishes. It basically shows how we can tune recursion to manage the trade-off between accuracy and compute cost. Then figure 6 looks at what happens if you have essentially unlimited compute. RINS still wins out compared to the baseline, but the gap narrows. So, recursion is helpful, but it's not an infinite well of improvement. What about vision tasks? Table 2 addresses that. Surprisingly, recursion doesn't offer a big advantage in a straightforward image classification benchmark. In fact, a non-recursive approach on higher resolution images performs better. So while RINS seems fantastic for language, it doesn't necessarily give the same returns in pure vision scenarios. They also touch on how recursion might work in multimodal models, like ones that handle both images and text. That's still open territory, and the authors suggest we'll see more details soon. Let's check how RINS does in real-world tasks. Table 3 focuses on zero-shot classification and retrieval. You'll see modest but consistent improvements in zero-shot classification on datasets like ImageNet, where even a 0.7% boost can be significant in these benchmarks. For retrieval tasks in Coco and Flickr, RINS pushes accuracy above 95%, outpacing the baseline by a few percentage points. Moving on, Table 4 shows multilingual results using Siglet models. RINS helps across classification, retrieval, and even cultural diversity metrics. Interestingly, stochastic RINS outperforms the standard version. The random skipping seems to reduce overfitting while still leveraging recursion. Crucially, they rule out simple overtraining as the cause. Models with the same dataset size still do better with RINS, suggesting recursion captures something fundamental, perhaps the self-similar structure of language. It's an efficient inference strategy that leads to better generalization. Finally, let's see how RINS scales with more compute. Figure 7 indicates that increasing recursion depth improves training efficiency and yields better overall performance. Up on the top graph, you can see that the scaling exponent, how performance changes as you add more compute, is higher with RINS than with a standard model. The bottom graph shows asymptotic loss, basically the best performance a model can reach if we train it forever. RINS lowers this limit, hinting at a structural advantage that you can't just replicate by overtraining a non-recursive model. In Figure 8, the paper explores the question, how many rounds of recursion are best? Larger models generally need more recursion loops to fully capitalize on their capacity. That part makes sense. If the network has more parameters, it can benefit from additional refinement. They wrap up by discussing how RINS fits in with other inference-time strategies, such as chain-of-thought prompting or self-consistency decoding. Those approaches often add steps after the model's basic output. In contrast, RINS modifies how inference is internally structured, looping in the middle of the process instead, and that seems to make a real difference without extra training overhead. Thanks for joining us today. Happy learning and stretching together.